For the next talk, we'll continue to look at WebRTC. The speaker is Wei Zhang. He has been serving as a senior engineer at ByteDance since 2018, and he specializes in real-time communication and low-latency live streaming. Okay, please go ahead.
Okay. Good afternoon, everyone. It's a great honor to be here. I come from ByteDance and Wei Zhang, and these are my co-authors. Today, I'm thrilled to share our latest work, harnessing WebRTC for large-scale live streaming. So here's today's roadmap. Let's begin with background and motivation. So live streaming has reshaped how we connect, fostering real-time interaction between broadcasters and viewers that were once unimaginable. But one critical factor underpins its success, low latency. So let me share two examples. First, the e-commerce. Imagine a flash sale where the first comment wins. Even a slight delay can cause viewers to miss the deal, leading to frustration. Second, entertainment. During live sports, if the stream lags, spoilers in the chat can ruin the excitement before viewers can even see the action. So these examples highlight why reducing latency is essential for enhancing user satisfaction and engagement. So to identify where latency optimization would be most effective, we broke down the delay into segments and focused on network-related delays. Our key observation is that the last mile latency dominates the overall delay, as you can see here. So with this insight, we prioritize the viewer-side delay optimization. So a simple way to reduce latency is just to lower the pre-buffering duration. However, this approach can lead to more stalls. For example, in an A/B test, reducing pre-buffering from 6 seconds to 3 seconds really lowered the latency by about 40%. However, it also causes a serious degradation. For example, the video store count is degraded by 82%. Although we optimize FOV to solve the store problems, the further improvements become increasingly difficult due to its TCP-based limitations. So this challenge motivated us to pursue a fundamental protocol upgrade. WebRTC, with its ability to deliver sub-second latency, seemed to be a promising alternative. To evaluate its potential, we implemented a preliminary streaming solution called Vanilla WebRTC. In our system, we also call it Vanilla RTM. In a one-week A/B test with 450 million view sessions, Vanilla RTM outperformed FOV on several key QoE metrics. For example, you can see here the end-to-end latency and the audio stores are reduced by more than 40%. Though there is a slight increase in the first frame delay. However, the Vanilla RTM had a significant negative impact on user engagement. The view penetration has dropped by 0.7%, and the daily viewing time has declined by more than 1%. So these results highlight the need for further optimization to fully unlock WebRTC's potential. So you might wonder why we focus so much on user engagement. Here's the reason. First, it reflects users' willingness to use the service. Second, it's closely tied to business revenue, as higher engagement drives in-app payments like purchase and tips. To measure the engagement comprehensively, we focus on two metrics, view penetration and daily viewing time. The view penetration is defined as the ratio of viewers who enter a live room to those who swipe past it. The daily viewing time is defined as the average time each viewer spends in live streaming per day. So optimizing only one metric can lead to trade-offs. For example, faster first frame delivery might boost penetration, but reduce viewing time due to more stores. Conversely, longer viewing time might result from loyal viewers compensating for low penetration caused by higher latency. So by optimizing both metrics simultaneously, we ensure balanced and meaningful improvements in engagement. So now that we've established why engagement is so important, the next question is, how do we improve it? Since engagement metrics can't be optimized directly, so I will explain how we identify the top QoE metrics that most influence user engagement. To quantify the impact of QoE metrics on engagement, we trained 2 ChargeBoost models using data from 150 million live stream sessions, one to predict the view penetration and another one to predict daily viewing time. We then analyzed the importance of each QoE metric based on the trained models. As you can see here, for view penetration, the most influential metrics are first frame delay and startup video store count. And for daily viewing time, the most influential metrics were AV drift and CPU usage. So interestingly, some results contradicted conventional wisdom. For example, the E2E delay had a low importance score, and the store metrics didn't dominate daily viewing time. So this is because WebRTC already significantly reduces latency and stores compared to FRV, shifting the remaining bottlenecks elsewhere. So these findings emphasize the lead to tailor optimizations to the specific context of WebRTC-based live streaming. So now that we've identified the key QoE metrics, let's dive into the core optimizations to enhance them. Our first optimization tackles the inefficiency in the vanilla RTM media pipeline, which was originally designed for the RTC. So the key inefficiencies include the codec initialization, and unnecessary audio processing blocks. In RTC, the codec objects are initialized for each view session, increasing CPU usage and delaying the first frame. Additionally, many RTC audio processing blocks, like audio mixing, are unnecessary for live streaming, where viewers don't publish audio streams. So these blocks add unnecessary CPU overhead. To address this inefficiency, we integrated the 2 media pipelines into a unified pipeline. First, we made the codec non-lived and reusable across streaming services. When viewers swipe between on-demand and live content, the same codec is reused, eliminating position initialization and reducing CPU spikes. Second, the G buffers now push frames directly out of the RTC media engine, bypassing unnecessary RTC-specific audio processing blocks. So this significantly reduces CPU usage. Our second optimization focuses on AV synchronization. The synchronization mechanism in vanilla RTM inherited from RTC was inadequate for live streaming due to the RTC prioritized ultra-low latency over strict synchronization. And RTC limits synchronization frequency and magnitude to avoid disrupting RTC. So here you can see an example. A moderate both loss and fluctuating RTT causes AV drift to persist for nearly 30 seconds here. We implemented a 2-stage synchronization mechanism to address the AV drift problem. In the first stage, the AV sync in WebRTC prefers loose AV sync. In the second stage, we designed a new audio calibrated AV sync model for rigorous AV sync. So here are 2 examples. So in the left example, if the audio is delayed, the corresponding video frame P1 should also wait to maintain synchronization. So an exception is if the first iframe, it would be rendered immediately to protect the first frame delay and view penetration. So for the right example, conversely, if the video frame P1 is delayed, the audio continues at normal speed, and video rendering is accelerated to catch up. Now, our third optimization tags startup stores due to the GOP cache at the edge CDN. Here's how the caching works. Each edge node maintains 2 levels of GOP cache. The load level cache holds each edge node maintains 2 levels of GOP cache. The load level cache holds only the most recent GOP, discarding old frames when a new GOP arrives. The per-viewer cache is created and initialized by copying the load level cache when a viewer joins. So as you can see, when new viewers pull the string, the cache GOP is flushed to them as startup, so creating a burst of traffic that leads to congestion and stall. So our solution is built limited startup pacing. First, we allow an initial burst at the start of a view session during a short startup window to quickly probe the network. Then we compute a very limited pacing rate for each view to smoothly drain the cache GOP, reducing the congestion and source while preserving the first frame delay. So now let's move on to the evaluation results to see how these solutions perform in practice. The first design, the integrated pipeline elevates CPU overhead and speeds up the first frame. Additionally, optimized CPU usage prevents devices from being overwhelmed, leading to reduced store metrics. More importantly, these QoE improvements lead to more than 0.2% increase for view penetration and 1% improves for daily viewing time. So these results validate our prior analysis and demonstrate the effectiveness of our optimizations. The second scan audio can liberate synchronization, significantly reduces AV drift. For example, the drift duration is reduced by 90%. However, this improvement comes with a trade-off. When the audio is delayed, the video waits, leading to more video stores. But since audio is rendered independently, the audio stores remain unaffected. So despite this trade-off, the daily viewing time is still improved by more than 1.6%. So this also aligns with our previous analysis. In our WebRTC-based stack, where baseline stores are already low, AV synchronization becomes a key factor for improving viewing time. So the third solution, the very limited startup, reduces startup store. Both startup video store count and store duration are reduced by over 8%. These gains boost view penetration by about 0.5%, which is also consistent with our prior analysis. To evaluate the overall effectiveness of our optimizations, we conducted a 2-week A/B test in Q4 2024. Comparing RTM with FRV, the results show that RTM significantly outperforms FRV across most key metrics. For example, the end-to-end delay is reduced by more than 50%, and the startup store metrics are all optimized by more than 60%. However, compared to FRV's colo-based TCP stack, RTM's user-space WebRTC stack slightly increases CPU usage by 0.15%. Additionally, without TCP's in-order delivery and long pre-buffering, RTM results in 8.1% more drifted sessions. On user engagement, RTM improves statistically significant improvements. The view penetration is improved by 0.03%, and the daily viewing time is increased by 0.39%. While these numbers may seem small, they are highly impactful for a mature platform like Douyin, the Chinese version of TikTok, so which handles billions of sessions daily. These engagement gains result in 0.8% more paid orders, which can translate to several billion in business revenue. So to further illustrate RTM's advantage, we measured the end-to-end latency during 2 major sports events, the World Cup 2022 and the Asian Games 2023, across Douyin and 4 other leading Chinese live streaming apps. The results show that Douyin powered by RTM achieved at least 3.5 seconds lower latency than its competitor. So finally, let me share some deployment experiences and our future directions. First, deploying RTM requires close coordination with the CDN providers. Second, we operate RTM and FV in parallel at present due to several challenges, including limited CDN support, RDP, UDP traffic blocked by some ISPs and organizations, and cost considerations, since RTM is currently more expensive than HTTP-based distribution. Additionally, we worked on supporting B-frames for higher encode efficiency. Finally, we focus on ingest side optimizations, as improvements at the ingest level benefits many concurrent views simultaneously. So looking ahead, we see several exciting opportunities to further enhance RTM and live streaming technologies, including the QoE modeling, the receiver-driven congestion control, and unified architecture and protocols. So to conclude, let me share a concrete illustration of RTM's advantage. Here is a recording of a sports game comparing RTM and FOV. Here you can see the upstream is RTM. The low string is FOV. The RTM is about 3 seconds ahead. So let me show it. Okay, as you can see here, the viewers on FOV could literally hear nearby RTM viewers cheering before they saw the goal themselves. So that's my sharing. Thank you.
Any questions from the audience? Okay, I know that the T ladder is also from ByteDance, right?
Yeah.
So I want to ask what kind of bitrate adaptation you use for this work, and have you considered adopting T ladder in this real-time delivery framework?
Yeah, probably. They can be combined. I'm pretty sure.
But what's the current ABR algorithm that you're using for
Yeah,
this?
currently we are working on the ABR. Probably T-ladder can be used.
Okay. Yep. Any questions from the audience? Okay, let's conclude. Thank the speaker again. Yeah, thank you.